Hey everybody, I hope this video finds you well. Today we're going to be working our way through section 2.4 from your textbook, starting to see the connection between matrices and systems of linear equations. To do that, we're going to introduce a very important definition for our class and talk about some operations on matrices that allow us to manipulate from one matrix to another while preserving sort of some fundamental structures. So to do that, we're going to talk about section 2.4, which is introducing row echelon form for matrices and also talks about elementary row operations. So to begin with, we've got a definition here. We're defining what it means to be in row echelon form. So a matrix is said to be in row echelon form if three conditions are satisfied. You have to have all the zero rows, if there are any, at the bottom of the matrix. The leading element of any non-zero row must be a 1, and any element below a leading 1 is a 0. So those three conditions are what it means for something to be in row echelon form. So let's take a look at the 6 matrices that we have below, all very different sort of shapes and sizes and everything. And we're going to try to determine which of these sort of fit the definition of row echelon. So let's start with this first one here, right? So this matrix here looks to be a 3 by 5 matrix, 3 rows, 5 columns. Let's see if it satisfies these definitions. So first of all 0 rows are at the bottom of the matrix. Well, are there any 0 rows? This guy does happen to have a 0 row. He's right there, and it is indeed at the bottom of the matrix. So first condition, all good. Second condition, the leading element of any non-zero row is a 1. Well, there are 2 non-zero rows here and here. What are their leading elements? Well, there's a 1 right there and a 1 right there. Those are the leading elements because those are the first non-zero values in those rows. And they are both 1s, so condition 2 is met. Finally, we need any element below a leading 1 to be a 0. All right, so if we take a look here, there's one of our leading 1s. Everything below it is a 0. There's our other leading 1. Everything below it is a 0. So it does satisfy that third condition. So this guy here is in row echelon. All right, let's take a look at this second guy here, right? This guy is a 4 by 2 matrix, 4 rows, 2 columns. So first thing we want to check are all the 0 rows at the bottom of the matrix? Well, are there any 0 rows? There are 2 of them. They are not at the bottom of the matrix, unfortunately. So this guy, row echelon, no, he is not. We could go through and check if he satisfies the other conditions, but it doesn't matter because if we're just trying to determine if something is in row echelon or not, row echelon form or not, as soon as one of those conditions is not met, we know it is not in row echelon form. All right, let's look at the third matrix down here. This guy looks to be a 4 by 3 matrix, 4 rows, 3 columns. Let's go ahead and check the conditions. All 0 rows. Well, are there any 0 rows? There is a 0 row, and it is at the bottom, so we're all good there. The leading element of any non-zero row is a 1. Well, leading element there is a 1. Leading element there is a 1. Leading element there is a 1. So we're all good, looking on track to be in row echelon form. Any element below a leading 1 is 0. Well, there's our first leading 1, and unfortunately, right below it is another 1. So this guy is not in row echelon form. All right, so this guy here failed condition 3. And I guess we can go back and just sort of make a note, right? This guy, it was on condition 1 that failed, and maybe some of the others. And this guy is condition 3 that failed. All right, let's go ahead and take a look at our fourth matrix right there. All 0 rows at the bottom of the matrix. Well, this guy does have a 0 row. He's right there. So this guy is all fine in that first condition. Leading element of any non-zero row is a 1. Well, it is, so we're all good there. Any element below leading 1 is a 0. Well, that is true, so we're all good. All 3 things are satisfied. This guy is in row echelon form. All right, let's do our fifth matrix here. That's a 3 by 3 0 matrix, 3 rows, 3 columns, all 0s. Well, interestingly enough, one thing you guys should sort of keep in mind is that this is automatically in row echelon form by default because you don't even need to worry about these conditions because there are no non-zero elements and all of the 0 rows are all of the rows entirely. So this is probably something good to just sort of keep in mind here, right? That zero matrix of any size is automatically row echelon. So that's sort of just a good thing to remember, right? The zero matrix always automatically in row echelon form. All right, our last one here, the sixth matrix, right? I got to check for 0 rows. Well, this time there are no 0 rows, so this first condition is satisfied. If there aren't any 0 rows, we don't need to worry about them being at the bottom. Next thing we need to make sure is that the leading elements of any non-zero row is a 1. Well, right here, there's our leading element. It's a 2, so it's not going to be in row echelon form. Notice that not only was this guy not a leading 1, this guy was not a leading 1, and this guy was not a leading 1. So this guy fails to be in row echelon form, and it failed condition 2. So these examples here, this guy, and this guy, all show you guys sort of what it means to fail one of the conditions. As soon as it fails one condition, it is not in row echelon form. So hopefully that gives you guys a little bit of an insight into what this definition means. What does it mean to be in row echelon form? So now what we're going to talk a little bit about is what happens to these matrices like this guy, or this guy that are not in row echelon form. You can sort of see that they're sort of maybe close to row echelon form. So is there a way to take something that isn't in true row echelon form and put it into row echelon form? So we're going to start to discuss that. So to do that, let's sort of go back to thinking about systems of equations. We're going to try to consider these sort of 4 systems that I've written out here. Now, it shouldn't come as a big surprise to notice that all of these have the exact same solution set. They all have the solution set x equals 3 and y equals 0, even though they're 4 different systems. And why is that the case? Well, let's take a look at the original system there. 2x plus y equals 6, 3x minus y equals 9. It's a 2 by 2 system, right? It's got 2 variables and 2 equations. So what's the difference between this first equation and this second system over here? Well, all that we've done is we've sort of interchanged the equations, right? This is system 1 with equations interchanged. And obviously, it doesn't matter which equation we write first and which one we write second in terms of the solutions. It's the same system. So for all intensive algebraic purposes, well, this system here is really the same as this. It's just written differently. All right, what about this third system right here? Well, you can see that the first equation is identical to the first equation, and the second equation is just a scalar multiple. All we did is we multiplied this equation here by -2 to get that equation there. So what we're sort of noting here is that this is just system 1 with -2 times equation 2. And obviously that's not going to change the solutions because all we've done is sort of taken the original second equation and said, what does it look like if we multiply everything by -2? And since we did it on both sides, balancing the equation, it doesn't change the equation, doesn't change the solutions to the equation, and therefore doesn't change the system. All right, the last one here maybe looks the most different, but keep in mind that there's a very strong sort of relation here. Right? If we look back at this sort of original one here, if you imagine taking this equation here, multiplying it by 2, you get something that looks like 4x plus 2y equals 12. What happens if you add that to this equation here? Well, if you add that 4x and 3x, you'd get 7x. If you add that 2y and -y, you'd get that y. And if you take that 12 and add it to 9, you're going to get that 21. So, in other words, this is system 1 with basically taking 2 times equation 1 plus equation 2 and popping it into the slot for equation 2. Now, that one might be the hardest sell, that it really has the same sort of solution set. But you guys are used to this sort of operation of combining, adding, and subtracting equations to one another. If you remember solving systems of equations way back from an algebra class, when you learned like the method of elimination. it doesn't change anything because all you're doing is you're saying, I know this relation 2x plus y equals 6 has to be true. So if I use that relation in the other equation, it's not going to change the solution set. So what is the point of talking on and on about all these different sort of systems of equations? Well, what this is trying to show you guys is that even though these four systems all look pretty different, they have the exact same solution set. So let's sort of think about what those operations that we know don't change anything in terms of the systems would look like in terms of matrices that represent these systems. So this first one here was talking about interchanging equations. So for systems, we know we're allowed to permute or interchange two equations. For matrices, if we were going to write a matrix to represent the system, as we talked about in the previous video, well, if we can permute two equations, that also must mean we can permute two rows. We can interchange two rows without really changing any of the fundamental structure. All right, this guy here was talking about multiplying one of the systems by a scalar or a non-zero constant. So if you can multiply an equation by a non-zero constant and not change the solution set, then you should be able to multiply a row by a non-zero constant without changing the sort of fundamental structure of that matrix. Finally, in this last one here, right, we added a non-zero multiple of one equation to another equation. Since the equations are represented by rows, we should be able to add a non-zero multiple of a row to another row. So we're trying to get you guys to see that these three sort of operations that don't change anything in terms of a system of equations should also be thought about as operations that don't change too much about a matrix. So we give these operations on matrices a very special name. We call these, jumped ahead really fast, man. We call these three things here the elementary row operations. And we often abbreviate that as ERO. So if you ever see reference to an elementary row operation, you're talking about either permuting two rows, multiplying a row by a non-zero constant. Wouldn't make sense to multiply by zero because then you just zero everything out and you'd get a tautology, which would be irrelevant for the system of equations, and adding a non-zero multiple of a row to another row. So those three operations consist of what we call the elementary row operations. All right, now we're ready to go on to that next page and talk about this sort of definition here. So, row equivalent. A matrix A is said to be row equivalent to a matrix B if you can transform A into B using only elementary row operations. Okay. So when we talk about a matrix being row equivalent to another matrix, what that means is there is some process to start with matrix A, perform those elementary row operations, permuting two rows, multiplying a row by a non-zero scalar, or adding a multiple of a row to another row. And you can use some combination of those operations to get to matrix B. If that's the case, then we say A is row equivalent to B. And in terms of notation, we often write A with a little squiggly line and B, saying that those two things, they're not equal. They're not the same matrix, but they're row equivalent. Now, as a completely sort of big aside, we could go through and if we were only interested in matrices and we didn't quite have as much of a connection to systems of equations, we could redo all of this talking about what it means to do elementary column operations and talk about what it means to be column equivalent to a matrix. But that doesn't really sort of match how we think about systems of equations. So we're not going to really dive into that. Everything we're going to be doing is based on row operations. All right, we've got this nice little theorem here. We've actually already talked about why this theorem should make sense. It says that the corresponding systems to two row equivalent matrices have the same solution set. And that should make sense. We constructed or came up with these elementary row operations by talking about operations that wouldn't change the solution set to a system of linear equations. So of course, if you use only elementary row operations, then those two matrices, their corresponding systems, will have the same solution set. So we don't really need a proof of this, right? Everything we did to sort of define the elementary row operations really constitutes the proof of that theorem. Instead, we're going to move on to another sort of important theorem about this. So the next theorem we're going to say is that every matrix is row equivalent to a row echelon matrix. So this sort of ties together the two big concepts that we've been talking about so far in this video. We started with talking about row echelon, what that form meant, and now we're saying that no matter what your matrix looks like to start with, you can use those elementary row operations to put it into row echelon form. Now, that actually is a pretty big idea, and it shouldn't be immediately clear that that's going to be true. So we will talk a little bit about a proof of that in just a moment. But before we do that, we're going to take a look at an example of what that process would look like. So in other words, we're going to try to take this matrix here, which is definitely not in row echelon form. How do I know it's not in row echelon form? Well, you can immediately see that there's a leading term that is not a 1. There's a leading term that's not a 1. There's a leading term that's not a 1. There's tons of things that violate the different parts of the definition of what it means to be in row echelon form. So this guy certainly is not in row echelon. But we're going to try to use some row operations, those elementary row operations, to put it into row echelon form. That, of course, won't prove our theorem, but it'll be an example of it. And we'll talk about the proof of the theorem in just a moment. So what would be our process to putting it in row echelon form? Well, there aren't any 0 rows, so we don't need to worry about putting any 0 rows at the bottom right now. But we would like to get the sort of leading elements of any non-zero row to be a 1. But we also have to keep in mind that once we get it to be a 1, we want to make sure that everything below it is also going to be a 0. So what we want to sort of do is notice that one of these guys should probably be up here, because that's going to be sort of the first leading value that we would want. We can choose any of them. For convenience sake, since we would like it to be a 1, let's go ahead and use that third row. So what we're going to do is we're going to make a little notation here. We're going to use our sort of squiggly line to say that it's row equivalent, and we're just going to keep track of the operation we did. We're going to interchange R1 and R3. So we're just going to interchange R1 and R3, which is one of those elementary row operations. So if we do that, we would now have the matrix 0, 1, 3, 2, 4, 0, 2, 6, 5, 6, and then 0, 0, 0, 3, negative 9, and 0, 2, 6, 4, 8. All right. Things look a little bit better now, because if we look at our sort of first row here, we do have that nice leading 1. But, of course, what we need is we need everything below it to also be at 0. So this guy is good, but there's issues in row 2 and row 4. So let's go ahead and take care of those. So we're going to do another elementary row operation. We're going to go ahead and take that row 2, which was one of the issues, and do row 2 minus 2 times row 1. So that was the third type of elementary row operation, where you said you could take a multiple of one row and apply it to another one. All right, let's see what we would get then after doing that. Well, that won't affect the first row, 1, 0, or 0, 1, 3, 2, 4. When we take 2 times that and remove it from the other one, we're going to get 0. And then, of course, 0. And then 6 minus 2 times 3 is also going to be 0. 5 minus 2 times 2 is going to be 1. 6 minus 2 times 4 is going to be negative 2. And then we have 0, 0, 0, 3, negative 9, and 0, 2, 6, 4, 8. Okay, that looks a little bit better. We still have an issue down here because there's our leading 1, and unfortunately there's something that's non-zero below it. So let's do another elementary row operation. Let's take row 4 and minus 2 times row 1. And let's see what we get there. Not going to change that first row, so 0, 1, 3, 2, 4, 0, 0, 0, 1, negative 2, 0, 0, 0, 3, negative 9. And when we do this, we should get 0, and 2 minus 2 times 1 is going to be 0. 6 minus 2 times 3 is going to be 0. 4 minus 2 times 2 is going to be 0. And 8 minus 2 times 4 is also going to be 0. Ah, well, this is interesting. We just got ourselves a 0 row here. We should check, is it at the bottom? It is, so we can just leave it there. Okay, so things are looking better. Is this guy in row echelon? Well, we've got a leading 1, everything below it, good. All right, we've got another leading 1, that's good. Everything below it, no. There's an issue right there. So we got to go ahead and remove that. So let's go ahead and do that. That'll be by doing row 3 minus, it looks like 3 times row 2 to help us remove that 3 there. If we do that, we should get 0, 1, 3, 2, 4, then 0, 0, 0, 1, negative 2, and then we should get 0, 0, 0. And if we do this, looks like we should get 3 minus 3 times 1, so that's going to be 0. And then negative 9 minus, let's see, 3 times negative 2. So that sounds like, what, negative 3 overall. And then 0, 0, 0, 0, 0. All right, so there we go. We got our sort of matrix almost there. Let's check if everything's looking good. Leading 1, everything below it is 0. There's a leading 1, everything below it is 0. There's a leading negative 3, so we got to do one more modification. Let's go ahead and take negative 1/3 times row 3, which we can do. That's the scalar multiple of one row. So 0, 1, 3, 2, 4, 0, 0, 0, 1, negative 2, and then 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. And we did it. This guy right here, well, this actually is in row echelon form. So what we did is we started with some crazy matrix back here, followed all these different elementary row operations, and got ourselves into something that is in row echelon form. This definitely does not prove that this can be done for every matrix, but this process that we sort of used here, we're going to formalize in just a little bit and talk about how it can be used as an algorithm to really do this for any matrix. Now, we do have one other very, very important definition to sort of mention here, which sort of relates about what we sort of meant by talking about the fundamental structure of these matrices. So, this definition, very, very important here. It's sort of a fundamental property of a matrix. So, we say that the rank of a matrix, A, written as rank of A, is the number of non-zero rows once A has been put in row echelon form. So, what that means is, in the above example, rank of A. Well, if we look back, you might say, well, how many non-zero rows were there? There was 1, 2, 3, 4. So rank of A is 4. No, totally ignoring part of the definition there, right? Definition says it's the number of non-zero rows once A has been put in row echelon form. So even though this is what A originally was, this is what A looks like if it's reduced into row echelon form. In that thing there are 1, 2, 3 non-zero rows. So the rank of A in the above example would be 3. So just keep in mind, rank is actually the number of non-zero rows of the equivalent row echelon matrix. All right, so let's talk a little bit about how we could sort of prove or justify that theorem that we stated. So this proof is a proof via algorithm. Your book lays out a very detailed explanation of this. We're only going to talk a little bit about it because it's not really a mathematical proof. It's more a proof via an algorithm. It says this is a way that you can always do what we sort of claimed. So what this algorithm says, I've sort of simplified it. Your book gives it in like 7 steps. I'm giving it sort of in 4 here to sort of help you guys understand a little bit. And then we're going to do another example sort of using this new terminology. So what the sort of proof says is that the way you should put something into row echelon form is to start by finding the leftmost non-zero column. So look at your matrix and find the first non-zero column. Then you call this the pivot column. And then you find yourself the topmost position, so just the top of that column, and you call that the pivot position. So you then use whatever elementary row operations you like to place a 1 in the pivot position. So you want to get a 1 in the topmost position of the leftmost non-zero column. Then you use the elementary row operations to place zeros below that 1. So notice that these first 3 steps here, basically what this does is it gets us a 1 and gets us, so a leading 1, and then it gets us zeros below that leading 1. Then what we do is if that does not put the matrix in row echelon form already, what we do is we repeat those steps, but only on the rows below the pivot position. So we sort of work from the top down, slowly sort of taking column by column until we have it in the right format. Your book goes through, again, a very, very detailed proof of why this algorithm will always sort of result in a row echelon matrix. But I hope as you guys do more examples of this, you can sort of see that this process is going to sort of work. So we've got another little example here, this 4x3 matrix, and we're going to try to very closely follow this algorithm here. So this algorithm says we're starting off with this matrix here. First thing we need to do is find the leftmost non-zero column. So this guy right here, that would be that column there. So this guy right here, let's go back and do that in a different color so it makes it a little bit easier. This guy right here, this would be what we call the pivot column. And, well, then we take the topmost position of this column and we call that the pivot position. So this right here, that is the pivot position. Okay. Now, once we've identified that, we say, okay, let's use those elementary row operations to get a 1 in that pivot position. Right now, a 0 is in that pivot position, but notice we could use either row 3 or row 4 to interchange and get a 1 into that position. Doesn't matter which one, so we'll just go out of convenience and use the closer one, R3. So let's interchange R1 and R3. So what we will then have is we will have 1, 4, 5, 0, 0, 0, and then we will have 0, 1, 2, and 1, 1, negative 1. All right. Then our algorithm says to use elementary row operations to place zeros below the 1 that is now in the pivot position. So we've got 0, 0, and then we have got a 1 down there. So we do need an operation. What we're going to do is we're going to use R4 minus R1. If we do that, we'll get 1, 4, 5, 0, 0, 0, 0, 1, 2, and we're taking R1 away from R4, so it looks like we should get 0, and then negative 3, and then minus 1, minus 5, looks like we should get minus 6. All right, so now we quickly check, is our matrix in row echelon? Well, we've got a leading 1, all zeros below it. Well, we've got this 0 row, and it's not at the bottom, so it's not in row echelon. So now what we want to do is we want to repeat 1 through 3, but only on the rows below the pivot position. So now we're going to be focusing our attention right in here. So we're only going to look at the rows below the pivot position. So we're taking everything up there and ignoring it, and now just working down here. So let's sort of rewrite that. I'm not going to do any operations. I'm just going to rewrite it so we can do our identification. 1, 4, 5. 0, 0, 0, 0, 1, 2, 0, negative 3, negative 6. All right, like we said, we're ignoring this row here. So now look for that first non-zero column. Remember, you're ignoring that top row though. So this is a 0 column to us. So we would actually identify this guy right here as the first non-zero column. So let's go ahead and circle that just like we did. this guy right here, he would become your pivot column. And this guy up right there, the top of that column, that would be your pivot position. Okay, so we now need to go ahead and use an elementary row operation to get a 1 in that position. So easiest way to do that would be to interchange row 2 and row 3. So let's do that. Let's do row 2 and interchange it with row 3. So we do that, 1, 4, 5, then we get 0, 1, 2, and 0, 0, 0, 0, negative 3, 6. Negative 6. Okay, so then we need to use the elementary row operations to place zeros below the 1 in the pivot position. So the issue is that guy right there, so let's go ahead and do that. That means we would need to take row 4 and add 3 times row 2. So if we did that, we get 1, 4, 5, 0, 1, 2, 0, 0, 0. 3 times that 1 is going to be 3, and that's going to 0 that first value out. 3 times 2 is going to be a 6, and that's going to 0 that value out. Okay, we now check, is this matrix in row echelon form? Okay, leading 1, everything below it is a 0. Leading 1, everything below it is a 0. And there are some 0 rows, and they are at the bottom. We're all good. This guy is in row echelon form. Okay. Now, the idea of this is that this algorithm here might not be the fastest or best way to do it. So when you guys are asked to put something in row echelon form, you don't necessarily need to follow this super strictly. You guys aren't computers or robots, hopefully at least, and you don't need to do this as step-by-step or algorithmically as this. If you see a faster way or a clever way, you can certainly go about doing it. But the reason we take the time to explain this algorithm and show it in this example is to convince you that if you were to apply this algorithm to any matrix, it would work. And since we know it would work, that means that every matrix can be reduced into a row echelon form, or that it is row equivalent to a row echelon form. As a side note, just to keep practicing our definitions here, this would tell us that the rank of our matrix here would be 2, because once we put it into this row echelon form here, there are 2 non-zero rows. All right, we're almost done with all this. We've got just a couple quick comments to make, a couple things about the sort of rank, and one extra little definition to finish up 2.4 here. So, couple little notes about the restrictions on the rank. So, suppose A is m by n. Then, you do know 2 things immediately about the rank. Rank of A is going to be less than or equal to m. I want to start with that. How do we know that? Well, what is the rank of A? It is the number of non-zero rows once it's in row echelon form. Well, if it's the number of non-zero rows, it certainly has to be less than or equal to the number of rows. And m is the number of rows. So certainly your rank cannot exceed just the literal amount of rows you have. However, even though maybe it's not as clear, also the rank of A is limited by the number of columns. Now you might say, why is that the case, right? I mean, this first statement should be very clear. The rank is the number of non-zero rows once it's in row echelon form, so it is certainly limited by the literal amount of rows. But why is the rank limited by the number of columns? Well, the rank is limited by the number of columns because of this algorithm here. This algorithm relies on using these pivot columns and these pivot positions. But there can only be a number of pivot columns or pivot positions that are equal to the amount of the amount of columns, right? A pivot column has to be an actual column. So that means you can only have the amount of pivot columns equal to the amount of columns overall. And since those pivot columns are where you're going to place those leading ones, which make it a non-zero row, that means your rank is restricted by that amount of columns. So it is very sort of important to remember here that the rank is restricted by both the number of rows and the number of columns. So you will never get a rank that exceeds the amount of rows or the amount of columns in your matrix. All right. Last sort of definition, which we're not going to use too much, but we do want to briefly talk about what is called reduced row echelon form. So a matrix A is in reduced row echelon form if, well, sort of dumbly, 1, it is in row echelon form, and 2, any value, oh, that doesn't look very nice, any element above a leading 1 is also 0. So a reduced row echelon goes a step further. What reduced row echelon says is not only does it need to be in row echelon form, so not 0 rows at the bottom, leading 1s in all the non-zero rows, and 0s below all those leading 1s, it also wants 0s above any leading 1s. So you have to have this second condition that says any element above a leading 1 is also 0. So just as a quick sort of example here, something like this, if you had something like 1, 2, 3, 0, 1, 0, 0, 0, this guy is in row echelon, definitely. Why is that? Well, he's got his leading 1, all zeros below it, leading 1, all zeros below it, and 0 row at the bottom. He would not be in reduced row echelon. Why is that? Well, as you can sort of see here, there's a leading 1, and right above it is something that is not 0. However, you could use an elementary row operation. You could namely take that R1 minus 2R2 and change it into something like 1, 0, 3, 0, 1, 0, 0, 0, 1. And that guy would be in row echelon form, and he would be in reduced row echelon form. Why would he be in reduced row echelon form? Well, now with that leading 1 right there, there are zeros below it and zeros above it. So he would be in reduced row echelon as well. Why do we care about reduced row echelon? Well, your book justifies it a little bit by talking about how when we get to using these matrices to solve the systems of equations, reduced row echelon makes it very easy to solve them. I don't really like that justification because, to be honest, it's pretty easy to solve systems of equations from both row echelon and reduced row echelon. Instead, probably the most important reason is this theorem right here. When you reduce a matrix into row echelon form, there are many row echelon matrices that a matrix is row equivalent to. However, if you limit yourself to this reduced row echelon, then there is only one unique matrix. So every matrix out there is row equivalent to a unique reduced row echelon matrix. So this right here sort of tells us that if we want things to be unique, if we want forms to be unique, we need to go all the way to this reduced row echelon form. In our next video, we'll be making our way into section 2.5 and seeing how this row echelon and reduced row echelon form of the matrix allows us to solve systems of equations. And more interestingly, from a theoretical perspective, we'll be seeing how rank right here actually relates to understanding the solution set of a system of equations.